Okay. Let's get started. Okay, so the last time I was a bit fast, so let's review. Let's recall what we have done. So we start talking about the process electrons. Then the positron goes to muon, to anti-muon. And then, so by using Feynman rule, we found this process, just applying Feynman rule to the diagram. So we obtained this one. If you forget about it, so you can just watch the previous lectures. And then we just do that. Since we cannot distinguish the spin polarization in the final state, and usually we average over spin initial states. So you just have a quarter in the 1/2 times 1/2, and then you have to sum over spin. And to do that, so what we did is the spin U bar P. So we use this one, spin, and also spin VP, P bar P, and P slash plus N. And then what we have is this guy. So that's what we found last time. And this process, and also this process, what we did is trace of gamma mu. Gamma nu is equal to 4G mu. That's what we used. And also, and GG minus GG plus GG. That's what we used. And then, anyway, so yeah. Do I need to write them? So that's what we use to reach to this expression. And from here, so that's what we used. So this one you already derived in the homework. And then what we did is that we used the central mass flame. So this electron So we took the central mass line like this way with an angle is given here. So of course here, and also we assume the ME is much less than mu. So that we ignore the mass of electron. That's what we did. And then, so therefore, the amplitude of momentum of muon is square root E squared minus M mu squared. And also K and so the Z is a unit vector on Z axis, and then theta is just the angle between E minus and mu minus moment. So then, if you use this one, so Q square is equal to, so Q square here in the denominator here, is indeed, this is P plus P prime, so therefore P dot P prime, and you can easily see that the P dot P prime is just a 4E square. As you can see, E square plus E square, and also times 2, yeah. Yeah, sorry, I think I missed 2. And then 2pk is it's super easy to do. It's p prime plus k prime. And then like this, eh? And then, so if you plug that one into here, so you can just find out that this one is equal to, it's simple calculation, numerical calculation. Like this. So that's what we found, and then the differential cross section is center of mass. We already know that this one is equal to like this way, and a quarter sum of spin and square, so like this way. So that's what we found like 2 lectures ago. Just plug that one into here, and then what we found is that this is equal to alpha square, and therefore ECM square square 1 minus M square, square, and then that. Okay, let's not write it down like this one. It's exactly the same. That's what we found, and let's see if there's I opened Tencent meeting. Okay, somebody wants Tencent meeting. Okay, lazy enough to come here. Okay. And so last time I think I made some mistake of fine structure constant. I think last time I did I put it in the video square? So it should be square. And of course H bar and C are hidden. So alpha is very important, often used in physics, but it's just a proportional E square after 1 over 4 pi square. Okay, so that's what we found. And then if you take it over, is equal to square so that's what I have written before. Okay, so that's the total cross section of this scattering process. And the important part is that apply Feynman rule, and then important part is reach this point indeed. That I already explained last time. Important part is to come to this point. But the rest of the calculation is just not that different. Okay, let's analyze this problem a little bit more. If you take this expression and furthermore high energy regime, high energy regime means the E is much better, bigger than mu. Therefore, essentially mu can take 0. Then this quarter sum of like this way. So you can ignore and mu equal to 0. So then it becomes 1 plus cos. And we would like to understand what this angular dependence. Angular dependence, if you take this center mass, the angular Sator, how does this quarter and square depend on this Sator? So we'd like to understand a bit more. So to do that, we just look at the helicity structure. So what we want to understand is that the angular dependence here is a bit more. To do that, so we like to understand helicity. Structure, want to understand. So to do that, so let's recall helicity and now the chirality is the same because we take the massless limit. Chirality is and helicity is the same if you take the massless limit. So as you recall, so you have the helicity and chirality is at the fermion. If you take, I think this direction is z direction now, and if you use the right spinner, right? So this is right-handed spinner or left-hand spinner. Right-handed spinner in z direction. So this is spin up and spin down. The corresponding. That's 1/2 minus 1/2 for electron for UP. That was the chirality, helicity at the massless limit, as you recall. So this one, so going to spin up and spin down. So that's what we can do is that we just insert like this one. So here, as you can, I think it should be P prime. So as you can recall, so this part is really coming from applying final rule in here. So B bar P prime is really positron, and then U of P is coming from electron, as you recall. And then, so this part, the purple part, is really coming from here, as you recall. So B of K is positron, the outgoing positron, and U bar of K, K prime, it should be K prime. K prime, strictly speaking. I hope I'm not mistaken. I'm not Am I correct? Sorry. I'm very sorry, I told you wrong. K prime here, sorry. So, B of K prime is really outgoing positron, and the U bar of K is not positron, so anti-muon, and this is mu. Sorry. So I just told you wrong. So this is the case, and suppose U of P electron is the positive chirality. What's positive? Right-handed. So right-handed electron. So right-handed electron is just this projection to right-handed electron is this guy. So as you did in homework, I call it this is P. Projection operator to the right-handed spinors, and then spinner, and then so this is indeed equal to. So the simple manipulation will tell you that this is equal to B dagger or P prime, and 1 plus gamma 5 over 2, and the gamma 0 and gamma mu U of P. So you just commute gamma mu and the gamma 5. And the gamma mu and gamma 5 always get, if you commute, as far as I recall, this gamma mu, gamma 5 is equal to 0. And please, if you want to take a look at the lecture note, please always look at the updated lecture note. As you can easily see, I often update my lecture notes. So therefore, if you commute to gamma mu, you get the minus sign here, and the gamma, if you commute to gamma 0, again you have the minus sign, so they have an overall plus sign. Okay? So therefore, 1 plus gamma mu, gamma 5 acts on B plus, then for positron. Okay? And here, so this looks like the right-handed positron, but in the case of positron, as you recall, so this is the plus and the minus assignment. So this is so that the C is equal to as you recall. Assignment this one, but on the other hand, so the plus 1/2 is assigned as the 0, 1. And the minus 1/2 is assigned 1, 0. Okay, that's the assignment for positron, as you recall. For spin is opposite for electron and the positron. So you have to assign the opposite way. So therefore, this will give you right-handed. This will give you right-handed electron. Let's go E minus, this part. On the other hand, this part is left-handed, the positron. So be careful. So therefore, so here we're looking at the process of the electron and the positron is just smashed each other. Are smashed to each other, but here in this process, if this is the right-handed, okay, then it has to be left-handed. Am I correct? Sorry, no. I mean, I don't know how does Peskin and Schroeder explain this one? I already forgot. Peskin and Schroeder. I think I should copy and paste the Peskin and Schroeder's. Sorry. Let me take a look. Okay, yeah, what I'm writing is correct. So this is correct. Okay. So left-handed. So always, so this is right-handed, and this is left-handed. Okay. So if the electron is the right-handed, the positron needs to be left-handed. If the opposite process, the amplitude will be 0. Okay. If this is right-handed, the amplitude will be 0. Okay, so be careful. And let's insert this one, and then we want to evaluate the quarter of m squared. Oh, sorry. I think I should include here is the quarter. Sorry, sum of spin. Okay. So we want to understand if the electron is the right-handed, what will be the amplitude? So that's what we want to understand. Then now, okay. Okay, so this is what we want to evaluate. And so you just apply this rule, or what that? So you just apply this rule. You just apply this rule, and this will give you, if you sum over all spin, and this will give you the trace of p primes. So now I take the mass of cement, so there's no m up here. Okay. So B and B bar will give you P prime slash 1 plus gamma 5 over 2 P slash gamma nu 1 plus gamma 5. So this is what we want to understand. And bring this one into right. This is equal to trace P slash prime gamma nu P slash gamma nu. As I mentioned, so there are 2 gamma here. If you bring this one to gamma here, it doesn't change. So if you bring it, it changes minus sign, and it bring to bottom right, you get the plus sign. And this is projection operator. P squared is equal to P. So therefore 1 plus gamma 5 over 2. Okay, so this is what we have. And then we recall this relation. So if you insert gamma 5, you get the epsilon tensor. And then I take the epsilon 0, 1, 2, 3 is equal to minus epsilon 0, 1, 2, 3 is equal to 1. And then everything becomes permutation symmetric. Okay. And then the plug. So one is just the usual algebra I have written over there. So we have to use this one. The other, we have to use the this one. And at the end of the day, what we get is the like That's what we have. Okay, we can do the same calculation for, so we just compute the this part of omega. And now we also assume that the so this mu plus has a left-handed spinner. So B of P prime, K prime, sorry. B of K prime has a left-handed mu plus, so therefore like this way, which means that the spinner is like this way, really. And right-handed means the like this way. So then, so we can do the same computation. So the spin, and then purple part. And you can do the same computation, and then what we get is exactly the same thing. Like this. That's what we have. Okay, so that's what we have. And then I have to erase somewhere. Okay, let's erase here. Okay, so I have to erase the. Okay. So what we have is that so we want to divide it in a square. Or spin 1/2 for this part. I think. So here E right minus E left plus 2 mu right mu left plus. So this amplitude is just essentially what you need to do is just multiply this and this and this. Okay. And this is indeed equal to quarter. Indeed equal to, so I'm going to skip this detailed calculation. I think in the lecture note I missed this part. I'm going to skip this detailed calculation. I don't think it's important to show the detailed calculation. Okay, let me do the following thing. 2 P dot K plus 2 P dot K prime. And so you have to be careful about when you contract with these two guys. And these two guys, when you contract it, so what we get is that the like this, eh? And in fact, so there's a rule that telling this epsilon tensor will give you the following contraction. This guy is indeed equal to minus 2 delta, mu delta mu sigma like this way. Okay, so this contraction of epsilon tensor will give you delta. So that's, you can just accept that, or you can, if you diligent enough, you can just take this identity we can derive. Then at the end of the day, so what you get is that the where are is equal to 16 e to the force q to the force p dot k prime, and then p prime dot k. And this is indeed equal to e to the force 1 plus cos theta squared. Okay, so that's what we have. Yeah. Huh? I'm sorry? This one?
Right. Right.
We don't have it. Do we? Huh? Can you tell me which one? Peskin and Schroeder said what? Essentially, I'm following in this section Peskin and Schroeder. Most likely, we need a quarter. We don't need a quarter. I think you have to be careful about the when you see the Peskin and Schroeder. Let's see. So at the end of the day, we would like to sum over everything, and if you sum over everything, what's going to happen? Let me check now. In total cross section is the no. I think it's typo of the Peskin and Schroeder. Anyway, I don't care. This kind of like proportional to something. No, I don't know. I think there should be quarter. There's something inconsistent with the. Okay, let's fix this issue later. What was that? I think if it is the case, it should be 16. Oh, there is no quarter. Sorry. Now that's not what it means. There's no quarter. This should be okay. Thank you. This should be okay. There is no quarter. Yeah. And this is the case. But let's analyze what it means. So there is no quarter, and I just missed the sum of spin in the lecture note. Let's look at what it means. So this means that the amplitude, when theta equals 0, amplitude becomes the largest. So this means that the cos theta equal to 1, this becomes the biggest, which means that the mu minus is, you just epsilon minus and epsilon minus and epsilon plus, you just interact, and the mu minus is going to z direction, mu plus is going to this direction. That is the largest amplitude. On the other hand, when cos theta is equal to -1, which means theta is equal to 180 degrees, so the E minus and the E plus, and the E minus is going there, E plus is, mu minus goes in there, and mu plus is going there, the amplitude becomes 0. Which means that from here to mu minus is right-handed, so which means the opposite, like this way, and the mu plus is left-handed. in minus left handed. So this process from here to here process the amplitude 0 because it doesn't preserve the angular momentum. The preserve the angular momentum spin. Do you understand? And this is spin up, and this is spin down. But on the other hand, here is spin down. I mean, in terms of z direction, spin down and spin down, like this. So therefore, this is yeah. So it goes to completely opposite chirality. So this is right-handed and then left-handed to the right-handed and the left-handed. So it goes to opposite chirality. So therefore, it doesn't preserve the conservation of the momentum. It violates conservation momentum. So therefore, amplitude should be 0 when theta equal to 180 degrees. Do you understand what I mean? Do you understand? On the other hand, if you have an angle, some angle, there is a superposition principle that there is a possibility to preserve the angular momentum. But if you go to the completely 180 degree, it doesn't preserve the angular momentum. And viable is the conservation angular momentum. That's why the amplitude should be yeah, conservation angular momentum tells you that the amplitude should be 0. Do you understand what I mean? Is it okay? Do you have any questions? Is it okay? Yeah, I mean, it's completely opposite. So here they spin up, and then here's, in terms of z direction, it's spin up, and then in terms of z direction is here now. This is z direction. If you look at the z direction, this is spin down, spin down. So therefore, it doesn't preserve the angular momentum. Okay. Any question at this moment? And then good. The differential for the cross section for massless spinner. Massless particle should be like this way. This just plug this one into here, and then just multiply some appropriate factor, you get this. Likewise, if you consider the opposite chirality to the final states, for instance, if the muon has a left-handed chirality, and the anti-muon has a right-handed chirality, and essentially what we need to do is essentially plug, what was it? Here you have a minus sign. You need to plug in minus sign here. If you plug into minus sign here, then epsilon, this one become plus sign. This become plus sign. This one become plus sign, and then so therefore this one become plus sign. This one become plus sign. So that's the difference. And then at the end of the day, so what we get is just a sign difference between one minus cos theta. So this also makes sense. We now change the chirality for final states. So therefore, here it becomes the opposite. The current becomes opposite. So in this case, mu has a right-handed one. So therefore, it has the no. Mu has a left-handed. Sorry, left-handed like this way. Therefore, like this way and like this way. So therefore, if you look at that, say this is say equal to 180. 180 degree. So then it has the same chirality as the wall. So therefore, the amplitude becomes the biggest, the maximum. On the other hand, if you swap mu minus and mu plus, this is theta equal to 0 case, the amplitude becomes opposite. So then in balance, so mu has a left-handed, so therefore left-handed means like this way. Yeah. So then it completely opposite from the initial states. So therefore amplitude becomes 0. Okay. So therefore if you look at the helicity structure, you can see how this cos theta arises. And you can also do the same game. This is equal to, this is also equal to, yeah. Like this, right? And if you sum them all the chirality up, so the cross term will cancel. If you square it, you have 2 times cos theta. Here minus 2 times cos theta. If you sum them up, the cross term will cancel. And at the end of the day, if you take 1/4, what you get is this one. This dependence cos square is really coming from this square of cos theta. Okay. And this cos theta governs the angular momentum conservation of this process. Okay, that's what it means. Any question at this moment? Okay, then. I will move on. I will move on to the cross-section symmetry again. So last time I briefly talked about cross-section symmetry. So unfortunately, I already erased, but so this process. Okay, so the cross symmetry is indeed this process to this process. Minus. Okay, so this process to this process, we just need to, just rotate 90 degree to the clockwise, and then, okay, rotate clockwise and just swap the directional arrow. Okay, so they, as you can see, if you do that, 90 degree E minus goes to up, but if you just swap 180 degree in the how to say, also on the blackboard direction, you get this direction, this one, and this process of the rotating this diagram, it just amounts to the P goes to P1, and then P prime goes to minus P1 prime, and then K goes to P2 prime, and then K prime goes to minus P2 prime, P2. So this is the really crossing symmetry, which means that the amplitude, if you compute amplitude this one, you don't need to compute amplitude here. It's the same thing. That's already what we did. It's what I explained. So therefore, this is the sum of spin m square. I'm very sorry. So I understand. Here, you don't need to sum over spin. Sorry. Do you understand what I mean? Here, I already specify R and L in the initial state, and the final state I already specify R and L. So therefore, you don't need to sum over spin. Sorry. So no need to. So it's already specified. So no need to sum over spin. So the directional is correct. I'm sorry. So no need to sum over because I already specified initial and the final state spin. So no need to sum over. Okay. And this is equal to like this. So it's super easy. So I already compute this one, so just plug this change of variable of momentum. So then what we get is the correct answer. Now, where should I erase? Maybe here. Okay. Okay. So then we introduce so-called one-dimensional variable. I think this one, this kind of scattering amplitude is the one-dimensional variable. I don't know. Can you search the Wikipedia or something? I think 50s as far as I recall. This kind of 1950, kind of, I think 1950 or 60, I don't know. Kind of lighter. And then SDU like this. And if you take mass of cement, so if you take mass of cement, then T is equal to, this T is equal to, of course, K square and P square is equal to 0. And K prime square and P prime square, K prime square equal to P square is equal to 0. So therefore, this is just a like this. So then you just look at this is essentially equal to, in fact, this is equal to S square. So as you can easily see, this is S, anyway, so this is P prime. So S is equal to, of course, 2 P dot P prime is equal to 2 dot K dot P prime. So as you can see, here is just a S square. And here P1, P2 corresponds to P1, I'm sorry, I'm telling you wrong thing. P1, P2 prime is essentially it's the same as U, U, up to factor of -2. And also P1 prime and P2, P1 prime and P2 is essentially U, up to some factor. And here it's just S, P1, P2 is just S. And we take massless limit, so we know. So therefore, this amplitude is indeed equal to 8 P4, and Q square is what? This is Q, right? Q is P1 minus P1 prime square, so which is the same as this guy. This guy. Therefore, this is denominator, you have a T to the square. Like this. And then, so here, it's super easy to see how to do that. If you just take 90-degree rotation, T, so this become T, but T become S, okay? If you just do the 90-degree rotation, this T become S, and the S become T. S is this one, is indeed become, S is this one, is just T. So therefore, we just swap these to S and T, so therefore, this is equal to, this will give you, let me erase here. So this will give you, is equal to, so you swap S and T. So this is the crossing symmetry. So essentially, move from one to the other, you just exchange S and T. Okay, that's the crossing symmetry. And now, so we just want to understand the relation between STU. Okay, STU. To do that, again we go to center of mass flame, something like this one. So this is Q2 to scattering, and all mass now are the same, which is equal to, I call it M. Okay. So we consider such a system. So E in the EZ oh, sorry, no Z. E and then E. Like this. Then you can easily see, you can do just honest computation. It's super easy. The first one is super easy because I mean, here you just P plus P prime square is essentially 2E square. Yeah. So yeah, 2E square. And this is equal to like this way. Okay. So the 2E square is only like the time component matters. The spatial component cancel. So therefore 2E square. And this is, I call it the E center of mass square. And then, so the rest of computation also super simple. So I call it, this is theta. Super simple. You have okay. So the difference between P, so this is P, and this is P prime, and this is K, and this is K prime. Okay, so therefore, what we have is that so this P is indeed equal to, I got confused. So how to get the, sorry, square, sorry, that's why. And then here P square and sine square plus P square cos theta minus 1 plus 1 square. Sorry, here minus. So you can do the honest computation of this case. And then what we have is that this is equal to minus 2P square 1 minus cos theta. And this is equal to minus 2P square 1 plus cos theta. Okay, let's derive this. And so this here P. Sorry, let me try to get the. I think this. I need to be careful about this P and this P. I think this P is indeed. This should be the case. Is it the case? Yes. It should be the case, right? Okay, so this is the case. How do you get so here P is indeed equal to, so this is equal to E. And let's see, P sine theta 0, for instance, if you take this kind of stuff. Okay. And if you take the difference between, if you take the difference between K and P, so the time component cancel, then you have a P sine square here, and then P cos theta minus P. So I think what I have written is wrong. Sorry. V hat And then this should be also, sorry, it's not massless limit. I take that all the mass is the m, so therefore it should be p, sorry. Okay. So now for the difference in z component, you have this one, okay, and this. Okay, so that's the case. So we'll see that the when theta. So the important thing is that the when theta equal to 0, so this is the important thing. When theta equal to 0, t becomes 0. Of course, because when t equal to when theta equal to 0, k becomes p. So if this vector aligns to z-axis, this vector is equal to this vector, right? Do you understand? So this aligned to theta equal to 0 means that the k becomes z-axis, and since all the mass is the same, so therefore k should be equal to p. So therefore it becomes 0. Likewise, this one, as you can easily guess, when theta goes to pi or 180 degree, becomes 0. That's also super easy to see. This now k prime vector goes to this 180, so the z direction, positive z direction. So therefore k prime and p becomes 0. Is equal. Okay, so that's the case. And the important thing is that if you something have s plus t plus u, and this sign cancel, and then we know that the this is equal to 2e squared plus minus 2p squared. And we know this is equal to 4 times m squared. So if all the mass is the same in two scattering process, so 2e squared minus 2p squared. Okay. So I have to correct my lecture notes because I mean here it's a bit confusing. So this is the important relation in Mandelstam variable. So this relation is very important. You often use in the later half of the lectures. So this is the important thing. If all the mass are distinct, even if all the mass are distinct, this is the s plus t. If you do the honest computation, this becomes mi squared. I stands for 1 to 4. So this relation holds. So if you're interested, you can derive it. So here, I assume that all the mass are the same, but even if all the mass are distinct, if you sum STU, it's just the sum of mass squared. So this is you can derive. So it's a beautiful relation. That's what the did you check when Mandelstam variable was introduced? Okay, nobody checked in Wikipedia. Okay, that was a relation. That's a relation of Mandelstam variable. Let's take a break. I think it's a good, and I'm going to talk about component scattering. Let me check when Mandelstam variable is introduced. 1958. Good. Okay, I'm correct.
Of the amplitude extent of sum and the left square.
I'm sorry?
Why we think they are the form like what we think is like calculate the conceptual.
we calculate this one.
Right. We will calculate.
And,
So what we
give me 1-2 minutes is difference.
right.
Because I mean, we know that each amplitude d sigma is equal to some kinematic factor of what? And then square. Like this one. So therefore, each section will give you so you need to sum up.
The question is that you want the m square equal to this one instead of this one. You know what?
Because each process will give you this.
Each process. Okay. Each process. Okay, that's okay.
You cannot mix this procedure and the other procedure. Okay. Somebody still don't pick up the homework. Is it yours? Okay. And then let's pick this. But I think taking video and then Tencent will reduce the number of students coming here. So which is good actually. If all the students come, it's too much in this room. Okay. Okay. So, I think okay. Let's take a break. 5 more minutes.
我真的不会，我太差了，是我太差了。
Okay. So let's resume. Okay. Compton scattering. So Compton scattering is also very important tree level. Okay, we can just is E minus goes E minus gamma goes to E minus gamma. Gamma means what? Photon. So gamma always stands for photon. It's not gamma matrix. So we like to evaluate this process at tree level. Yep. So this process, so I'm going to be kind of brief because then it's not so difficult to evaluate. I mean, it's the same process, but we have to use some technique for the photon polarization. That's the most important point of this subsection. So this part is P minus Q. Okay, so this is the process we are considering. So there are two processes that contribute to this tree level amplitude, and then again we will do the apply the final rule. It's a super easy process. So essentially what we need to do is, okay, anyway, I'm going to be very schematic because I mean, you guys already know what to do. What was that? What should I do? Gamma mu. Okay, I think, okay. And then the same one. Okay. So the first one is the x variable. This is x variable, and the y variable, or whatever. And 1/4 is just 1/2 will cancel with the swapping x and y. Okay, let's do the first one. First one, you have a premium propagator here. So what we need to do is something like this one. Okay, we need to do this one, and this one is contracted with electron, and this one is contracted to the outgoing electron. And then the same thing. So the nu is contracted like this way, and the mu is contracted like this way. So this is final state. I'm not going to write down everything. So this is essentially what we have is the let's see, p prime k prime. Okay. Then the P prime, K prime. And here, I assume P and K. So then, more precisely, like this way. See? That's the first one. The second one, anyway, you already get used to it, right? I hope so. Size contracted P, but now this guy, this part is contracted K prime. So therefore, this guy should contract K prime. Okay? You understand? You already get used to it, right? And then the propagator is the same. And the mu is contracted here, so mu is contracted K, like this way, like this way. And then psi bar is contracted like this. That's how you get the. Okay. Now for the yellow, okay, let's write in yellow. Okay, I don't want to. Okay, then so now for this is equal to the first one is the u bar p prime, and then if you contract with the mu and the k prime, you get the polarization vector. And start because it's at outgoing, and you have the propagator of ferment, and which has momentum p plus k. Therefore, it should be p plus So this is the first one. As you can easily see, Nu is contracted K, you get the polarization vector. Psi is contracted P, you get the U of P. So that's final rule. You just apply. The second one is just a U bar of P prime. The same, but here minus I E element nu E nu of K. So now I just rename mu as a nu, and nu is contracted K. Then you get this one. So I just rename mu to nu because I just want to have for K is the okay. So I think I should call it this one is equal to nu K nu. And K nu, okay. Then polarization vector K prime mu, and K prime mu. So this is a polarization vector. And now in the propagator has a moment of P minus K prime, so which means P slash minus K prime slash plus M P minus K square minus M square. And minus IE I think my note is missing some part, but anyway, so you understand. So this is the second one, the purple one. Okay. Okay, and then let's sum it up. Then it's super easy to. Okay, and then this is equal to minus I E square E mu slash K prime E nu K U bar P prime. So that's you just sum them up. Okay, and then so we just recall that P square and is equal to P prime square is equal to mass of electron, and K square is equal to K prime square. This photon, which is whose mass is equal to Z. So, and also if you act P slash okay, let's see. Let me think. Okay, and also we need to use the critical algebra to simplify a little bit more. So for instance, P slash plus M and here, so this is P mu. Let's see, P mu gamma. Let's see, P. And again nu, and if you swap gamma mu and gamma nu, so you have to, if you swap the gamma mu and gamma nu, you have to apply critical algebra, and then critical algebra will tell you that this is equal to P mu times gamma mu minus sign plus 2 times G mu nu and plus M gamma mu acts on U, sorry. Acts on U, and acts on U, acts on U. And this is equal to 2 times P nu minus gamma nu P slash acts on plus M, sorry, minus P slash acts on M acts on U. Okay, that's the case, and we can ignore this one because I mean this is just equation motion. Okay, it's just Dirac equation which is equal to 0. So what's left is this guy. Acts on U, and this is equal to 2P nu U. So therefore this guy. I'm lazy, so I'm going to use this one. So denominator is essentially P square is equal to M square, as I mentioned. So M cancels with this, M square. M square. So M square cancels with M square, and K square is equal to 0. So therefore, denominator becomes 2 times P dot K, and with minus sign. Oh, there's no minus sign, sorry. And here, denominator becomes minus P dot K prime. And then we apply, I think I missed something. So here, it used to be this and gamma mu, This is the case, I made a mistake. Now we apply the P slash acts on P slash gamma nu, and U is equal to that guy. And then what's left is that okay, so lots of mistakes in the lecture note. So what's left is the following. So this is K slash. Okay, I will correct in the typo in the lecture note. And plus 2 gamma mu P nu. And then here, gamma nu minus K like this. Okay, so that's the application of this identity. So this is a simplification we made. Okay, and now, so we want to take this m squared. So this is just I times m. This is I times m. And we want to evaluate m squared again. And then we would like to use some technique. Now I can erase this diagram. It's yeah. The story is getting much more interesting than the free field. But as the story gets interesting, my energy, I'm getting more tired. Yeah. Okay, so we want to evaluate m squared. Okay, so we want to evaluate m squared. Okay, so to this end, we would like to use some trick to evaluate m squared. So we just write down that the amplitude m as like this way. Okay. Like this. Okay. And we recall that this is photon polarization. And we know that this is a photon polarization. And we know. So we just separate. So this part is photon polarization. And I think I hope it's visible from the back. Photon polarization. And we know photon polarization only we have to get rid of. So this one only have the transversal polarization is physical. We know is physical. Physical. So therefore, if you contract with k mu dot m mu, this should equal to 0. So for instance, if the so this will get rid of. So if you impose this one, this is called word identity. If you impose this word identity, so if E mu of k is equal to k00 k, if this is proportional to k mu, the amplitude becomes 0. So this is I call it a spurious. How do you pronounce spurious polarization? I call it spurious polarization. So if the E mu polarization is proportional to k mu, so this is I call it spurious polarization. But if you impose this one, you can just get rid of this spurious polarization. Do you understand what I mean? So for instance, if k is equal to k 0 k, then the polarization of proportion of this one is I call it spurious. Then the k times M0 of K should be 0. So this is the word identity. Okay. If this is the case, you can get rid of this spurious polarization. Okay. So therefore, there is no contribution from spurious polarization if you impose word identity. So therefore, this means that the M0 should be equal to M3. Okay. Then, for instance, if you sum over M square means sum of epsilon mu star and epsilon nu and mu. I think it's better not to write down that polarization. M nu star. Okay. If you do that like this way, and this means that the so if you only sum over transversal one, transversal means mu is equal to mu and nu should be 1 or 2. Okay. Then what you get is that this is equal to M1 square and then plus M2 square. Okay. But even if so, this is the case. The cross term will cancel, in fact. So this is the this should be polarization vector for photons. So therefore, the it can be the the complex variables, and then if you take the cross term cancel, and what you have M1 square and M2 square. But we know that the M0 is equal to M3. So therefore, what you can do is the M1 square plus M2 square plus M3 square and minus M0 square. You can do this kind of stuff. Okay. Even if you add this one, since we impose word identity, M1, M0, and M3 should be equal. Okay. Therefore, it doesn't affect the result. And this is indeed equal to G mu nu M mu and M mu star and minus sign. Okay, minus. Okay, so therefore here what we have is that in fact, one can replace the sum of the photon polarization is indeed equal to minus G mu nu. So you can just replace, if you impose this water identity, sum over polarization, sorry. That's why. I think it's not the mu and nu. So mu and nu should be sum of everything, all polarization. Sorry. This polarization vector lambda and lambda prime, in fact. So that's the meaning, polarization. Sorry. Okay. If you sum over all lambda and lambda prime, you get this. You project to the sorry. So this is polarization. If you sum over lambda and lambda prime, you project to the transversal polarization. Yeah, sorry. I think as you recall, and this is equal to just if you add the so water identity. will tell you the just replacement of all the spin polarization of the photon polarization vector. It's essentially replacing E nu to the minus G mu nu. Sorry, I think there are lots of typo in my lecture note. It should be minus G mu nu. I will change the lecture note later. Sorry about that. Okay, so that's what we need to apply essentially. And the derivation of this one will show up later by using. So this one you have to wait a little bit. So this derivation you can use the so-called path integral and so on. And this derivation is called Takahashi identity. I mean, anyway. So derivation I will give you later. So first you have to accept this one to get rid of this spurious polarization. But this derivation will be given at the end of the lecture. So you have to wait. So essentially what we need to do is just replace the polarization vector sum by minus G mu nu to compute the m squared. To compute m squared. Okay. And then the rest of computation is just straightforward, just tedious but straightforward. But one has to do. To be honest, I think. Okay, let's start here. Order sum of polarization. Again, if you do the polarization, so here you have a U bar P prime, and then you have to map a U by P prime, and then its complex conjugate, which is U. Okay. So again, you need to use this kind of stuff. We know that the last time I explained that if you take complex conjugate, what was it? So B slash gamma mu U and the complex conjugate is essentially equal to U bar gamma mu and B, right? So this I already explained last time. So you have to use this kind of trick to multiply to compute m square. You have to make m star. So therefore, what you get is U bar gamma mu U here, for instance. But you have to apply this rule, okay? And multiply. And at the end of the day, so this factor will give you the propagator like this one. And trace. In the middle, you have the identical factor. Gamma mu, gamma mu, plus 2 gamma mu. Okay, I think it's better not to write down the explicitly. Let's call this guy. Is, I'm lazy, so this one is equal to, let's call T mu nu. T mu nu. T is a bit strange, so S mu nu. Let's go S mu nu. So then S mu nu here. Okay. I'm lazy, so I'm a lazy person. So S mu nu. And then this guy will give you again another propagator. Not propagator. Sorry. The equation motion. I mean the orthogonality will give you this kind of Dirac operator. And where am I? And then S rho sigma. Sigma rho. Okay. So that's what we have. Okay. I call it this guy is S mu nu. Okay, good. Then you just do the computation. If you do the computation, what we have is that we can just decompose this one as the 4-part pieces. I mean, you just need to do computation. I mean, unfortunately, as a physicist, you have to do lots of computation. Unfortunately, lots of this kind of like a tedious computation. If you don't like to do that, I mean, it's better not to study physics. Okay. I think there's a typo in my lecture note. Sorry, let me check the Peskin shutter. Sorry, there must be typo in my lecture note. Oh, it's okay. Okay. Or does Peskin shutter have a typo? I don't think so. It's okay. It's okay. It's okay. I mean, this is almost identical. My lecture notes are almost identical to Peskin shutter. Almost copy and paste. So, so if you recall, so this 2pk square is essentially this square. Essentially this square and contract with G mu nu, G and G. And there's a two cross term, and then this square. That's what it means. So there's a 4-part, and that will give you. And you can easily see that the so one this one is related to k, and the k prime is swapped. As you can easily see, so this square is essentially you use k here. On the other hand, this square is k prime here. Okay, k prime here. And I think I missed minus k prime. So this is minus k prime. Sorry. Minus k prime, and the cross term is always give you the same. So therefore 2 is equal to 3. And then you have to evaluate 1 and 2 in that case. 1 and 2 here, and then I will use Mandelstam variable since now I don't need to write down explicitly in this diagram. So this Mandelstam variable is indeed B prime and two P plus K. Okay, so use Mandelstam variable to write down 1, 2, 3, 5, 4. Okay, so then here you have the minus 2k prime dot p plus m squared. Okay. And in fact, this is equal to a much simpler one, minus 2k dot k prime, 2p dot prime k prime, like this. explanation variable, I just give you an answer. Answer is written in the lecture note, so you have to do, this is the exercise. Exercise is a very good exercise. Exercise. So 1 is equal to 16 to m4 to the fourth m square. This is indeed appear in homework 5. Derivation is the homework 5. And this is equal to 1, and s and u are swapped. And 2 and 3 is equal to minus 8 for m to the fourth and square s minus m to the square plus m square yeah, m square u minus m square. So this is the derivation is appear in homework 5. So you have to do, unfortunately, this kind of computation. Okay. So these 2 and 3 are this is a homework. Okay. And then, so we know STU is just given by here. Then we just need to write down. Explicit form of m square. So I think okay, quarter sum of m square. And all the polarization, spin. Did I write the word? Well, this is not polarization. Polarization is sum already over, so this means the spin of the electron, spin of electron. Spin. So is equal to So anyway, so this is exactly what the reaction will tell you. And then this derivation is also homework 5 indeed. You have to derive this one from, plug this one into there, and then just massage the form and derive this one. Square and this one. So this is also exercise. And now we want to compute the differential cross section, the signal. Okay. But now, usually in this Compton scattering, what we need to do, so usually so far 2 to 2 scattering, we take this center mass frame. Center mass plane, usually, so far we take the center mass plane, but here we use a different frame. So it's so far, but now we take lab plane, so-called lab plane. Okay. Lab frame. So lab frame is that so we have the photon is just hit the electron, which is just at the rest frame of the electron. That frame is just the rest frame of electron. So this is P is equal to mass, and the momentum is equal to 0. And K is just omega z half. And then, so we have so this is called rough flame. And then, oh sorry, electron is mapped to P prime, which is equal to E prime, and then P. So like this way. I'm not gonna go into so much detail about the computation. It's just everything. I have written everything on the computation. You just need to derive. Just follow. But I think I already gave enough detail in the lecture note. So I just give you the final answer. So first of all, if you take I'm not going to give you all the detail. So the relation between omega and omega prime is given by, so this omega is the energy of photon, initial photon, omega prime is the energy of the final photon. Okay? Since they interact with the electron, there's some change from omega and omega prime. And this one's given by just 1 plus omega m 1 minus cos theta. So this is the relation between initial energy between initial and final photons. And then, as you know, so to evaluate the omega, so we have to have the relation between this Lorentz invariant phase space with this angle theta, or what's it? Theta, angle theta. And this one will give you given by 1/8 pi. I'm not gonna. So everything written in the lecture notes, so it's better to read. I think if you write down everything, it just make you bored. So I'm not gonna do that. So the relation between this angle and Lorentz invariant phase space is given by here. So the derivation is all in the lecture notes, so you should follow the if you want to derive it. Now we plug into this ordinary, the one I already saw you. Okay, so then the sigma d cos theta. Now, as you know, this is equal to this d omega. D omega is essentially d sigma d cos theta d phi, and you can just easily integrate over d phi, which will give you 2 pi. Okay. So now for the sigma d cos theta is equal to 1/2 omega 1/2 m So this is a general formula for this in lab flame for the complex and plug this guy into here. And then manipulate the computation. And what we end up with the, let's see. So here, so to be careful, in this lab line, P dot K is equal to easily derived at the m times omega. You can easily see P dot K, or what's a P? P is this guy, and K is just m times omega, and P dot K prime is equal to m omega prime, m omega prime. Okay. P dot k prime is m omega prime. And then just use this kind of relation. Oh, actually everything written p dot k and p dot k prime. So therefore, just plug that one into here, and then what you end up with is that the I think I made lots of typo in the lecture notes, and then pi alpha square and square omega prime omega and square and omega prime omega, and the final answer is very simple indeed, and this is called Klein-Nischner formula. Oh my goodness, I don't know how to write them formula. This was derived in 1929. We are still doing the physics in 1929, unfortunately. This was derived in 1929. This is only 4 years after the Heisenberg started the quantum mechanics. Okay, so that's the formula of compound scattering and tree-level amplitude. Any question at this moment? Okay, so this derivation is homework. After that, it's super easy. So it's your work to do that, to derive this one. So as you can easily see, when z equals zero, amplitude, as you can easily see. So when z equals 0, amplitude becomes biggest. Okay? That's easy to see, because sine z equals becomes 0. So this is, so which means that if photon just goes straight, then goes straight, and the relation between omega prime and omega is just given by this z equals 0 means the cos z equals 1. So therefore, omega prime is equal to omega. So therefore, let's see. Z equals 0, this is 0, and omega prime, omega is equal to omega. Okay. And the electron doesn't move, which means, okay, electron doesn't move. So which means that when Z equals 0, electron doesn't move, so it just goes straight. Yeah, so this is 1, and this is 1, and this becomes 2. Okay, so it's a super easy formula. But when Z equals to pi, the amplitude also the okay. Z equal to pi is the same, so they just go backwards. But the omega prime and omega is the relation become much more complicated because cosine z equal to -1, so this becomes 2 when z equal to pi. So therefore, omega and omega prime is the relation is a bit more subtle. So then this electron is just, the photon is just scattered by electron to the backwards, and the electron just go to the z direction, positive z direction. The amplitude will give in the, like this. And it's kind of like a property of this, the analysis of this formula is detailed explanation is given in the Peskin and Schroeder more. So I will just relegate it, the explanation to the Peskin and Schroeder. So this polarization and so on, everything, a detailed explanation is given in the Peskin and Schroeder, so I'm not going to explain it. Any question at this moment? Okay, so any question at this moment? Okay, so what we learned is a tree-level amplitude in QED. Tree-level. So what we learned is E plus and the mu minus mu plus. So we learn, and also in homework 5, we learn Baba scattering. I think I omitted, some of the students already did this homework. But anyway, so yeah. So this kind of stuff is really the, I mean, Babak scattering is essentially E plus E. Yeah. Anyway, so you see the homework. This kind of stuff is really, so the Klein-Nishino formula is 1929. Babak scattering around the 30s, around early 30s. So this kind of tree level is around the early 30s. Everybody already understand early 30s, 1930s. So this kind of stuff is already understood in the early 1930s. So, but after that, there is not so much progress in quantum field theory till Feynman, Schwinger, Tomonaga has developed in this perturbation theory, and including Dyson's. So now, from early 30s to I would say 1947 or 8. Not so much progress in quantum field theory. I think one of the reasons is World War II, I think. Because of World War II, the scientists need to spend more time on this kind of issue, so they couldn't focus on the research, and also there's not so much interaction between countries at that time. So therefore, the physics doesn't move on. So this is side effect of the war. I think that's what I would imagine. I don't know anything. I think that's my guess. So now then there's not so much progress, and as I mentioned in the first lecture, and then 1948, 7. This sorry. I need to take a look at 7. I think 7. 7. Shelters Island, the conference and so on. They just exchanged their progress during the World War II, and then perturbation theory in one loop diagram was successfully formulated in QED. That's what we are going to learn. 97 Shelters Island. Then from here, so-called one loop correction. So people develop one loop quantum correction. The technique in QED. And then the first main persons who developed is the Julius Schwinger, and then Feynman. Let's do the alphabetical. Feynman, and then Tokunaga. Independently developed, but their formulation all equal, which is shown by Dyson. And their Schwinger and Tomonaga's calculation is super involved. And then I think currently nobody uses their method. I think the current formulation is given by Dyson, and we are learning Dyson. And the Feynman give you the pictorial understanding of this Dyson theory. But anyway, so these 4 people essentially successfully formulated this how to evaluate one loop quantum correction, and this is the highlight of QFT1. So this is what we are going to learn. So far, what we are doing is really like a preparation of this the most important part of the QFT1. So this is the most important one, and it's highlight. of QFT1. So we are going to learn the most important part of the this course from now on. Okay. Okay, let me give you an idea of the okay. So is there no good choice? Okay. So one loop correction on QED, and then I would say so-called renormalization. So before doing the detailed computation, let me give you some brief, rough idea of what's the meaning of one loop or quantum correction to the three-level amplitude and renormalization. Just rough idea. Okay. So rough idea. So this is not written in the testing, but anyway. So the QED Lagrangian is given by f mu square plus minus n0 and psi minus e0 psi over gamma mu psi n mu. Okay, and then lots of typo in my lecture notes, and I just leave this blackboard as it is and then move on to In fact, this Lagrangian is called bare Lagrangian. This is not so meaningful Lagrangian actually. What I have written is that this is called bare Lagrangian. That's why I put the M0 and E0. This usually cannot be measured at an experiment. The reason why is that for instance, let me give you so-called one particle irreducible. Let's see. I don't know why it's called one particle irreducible. Okay, anyway, one particle irreducible diagram. So usually people call 1pi. So you have a propagator. For instance, electron propagator, we have written like this way and a sign. This one is equal to, so in the final row, this is equal to I p slash plus m p square minus m square. Okay. But on the other hand, so we know that we have this kind of in QED, this term, interaction term, will give you this kind of diagram. So this kind of diagram. If you use this one, this will receive lots of quantum correction like this way. This plus the first diagram is like this way. Photon will give you one loop, and also you have like this way. And also we can have lots of diagrams like whatever. Anyway. Lots of diagrams, and then you can have many things. I mean, as you can easily see, I mean, lots of group diagram one can create from by using this vertex. Okay? And one particle irreducible that you cannot cut in the middle. For instance, this is one particle irreducible, but this is not the one particle irreducible. Let's see. anyway, so this kind of diagram is maybe, I don't know, I'm not good at drawing this kind of stuff. So this is not the one particle irreducible because you can cut in the middle, right? You can cut in the middle, in the propagator, cut in the middle. So this is not included. Therefore, this is not include one particle irreducible. It's not the one pi. Irreducible, one particle means I think one particle propagator, and the irreducible means you cannot cut in the middle. That means I think one pi. That's my guess. And then, so this diagram, so we call this one is usually, if you sum all possible diagrams, we could write down one pi, like this one. I think the lecture note is that somehow arrow is opposite. I don't know why, but anyway. So therefore, all the quantum correction is essentially the sum over all possible one particle irreducible. The quantum correction to the propagator is this guy. So okay, so I think I don't include this one. Leading order I'm not going to include. So this is the one particle irreducible plus one pi plus one pi and so on. Plus one. So you just repeat it, like just add one pi diagram. That is the essential whole diagram, and then so this is called M0. So this is M0, M0. Well, more precisely, this is I call it P/-M0. Okay. But if you include this all possible one pi, this will the location of pole will change. We will learn. And also, location of pole will change. So the M0 and the M will be different. Okay? Moreover, you include the residue of this pole is no longer 1. You have, I call it Z2, plus analytic term. So the pole of this, if you include all the quantum correction, the pole of this propagator is no longer M0. And the residue is no longer 1 or I. Okay? So therefore, if you include quantum correction, the mass will change. Electron mass will change. And also residue will change. The same thing will happen in the photon propagator. Okay, so this is, I think it's going to be much more interesting, much more intricate from now on. And so far, it's just a preparation for this section for renormalization. Usually QFT1 course, most of the anyway, so average QFT1 course do not going so much into detail about this kind of one-loop quantum quotient renormalization. But anyway, that's very tricky. So this is the most important part of the QFT. The photon propagator, so we have again minus I g mu nu, and then I call it Q or something? Yeah, Q, maybe in this direction, I don't know, whichever is okay. Q squared. Anyway, I'm not going to write down plus epsilon. Always plus epsilon is assumed, but I'm going to omit the plus epsilon most of the cases. And this one will receive the again quantum correction, which is the 1 pi, and then plus. Now, for instance, this includes this kind of diagram. Okay. Include and 1 pi and 1 pi. this is the heart of quantum field theory. So and if you include this kind of all quantum correction, this will become something like this one. Again, if the massless is okay, but the form will get some mu. I call it mu. G mu plus analytic term. Analytic terms. Again, residue is no longer G mu, it's standard G mu. There's a constant will show up. So therefore, we need to. So to get the usual Feynman rule, so we usually mention that you apply this propagator is the I over, and this one is I over P slash minus P M0, and then and this is equal to, this propagator is I G mu Q square over Q square. But this, if you incorporate this quantum correction, this is no longer true. So therefore, we should. So this is the field should be rescaled in such a way that this for instance residue is just ordinary one or I whatever you call it, just a standard one. If you rescale G3 square root mu renormalized, and then psi is equal to square root Z2 psi r. Okay, so if you rescale it, so we know that this guy is equal to time order mu and nu. And this one is time order, time order psi bar and psi. So therefore, if you rescale the square root z, both psi and psi bar, anyway, so that's the same thing. Okay, psi. Psi bar and mu, so you can cancel with this Z2 with this Z2. Okay, you can cancel if you use the psi bar. Okay, so therefore, so this is called sometimes this. I mean, sometimes this Z2 called P strings renormalization or wave function renormalization, whichever it's called. Okay, I don't know. Physicists always coined some new word. Wave function renormalization, or sometimes called field strength, which I don't know. Both are all commonly used. Renormalization. So if you rescale and use this psi r and ar, then the propagator do not just correct residue at the pole. And then, so therefore, well, we need to rewrite this Lagrangian as follows. So if you rewrite this one, what we have is 1 over 4 C3, and then F mu nu R square plus so just rewrite this renormalization field, and this is much more physical field, can be understood as a physical field, because we cannot zoom into so much detail about this quantum correction. So therefore, it's better to use the psi r and ar instead of this bare. It's called bare field, and this is called renormalized field. It's much more physical field, and then we just rewrite everything in terms of then what we have is that so we just rewrite. So Z2 times M0 is equal to M. So it's much more, and then Z1, Z2, Z3, square root E prime, E0, E0 is equal to E prime. So we just rewrite it this one like this way. And moreover, so we write this one is equal to Z1 E. So this is E is physical E, and then physical E and bare E is related by this relation, and this is physical mass and this is bare mass is related this relation. And then writing, so since we have this constant in the Lagrangian, so we just split this Z I is equal to 1 plus delta I. So we just write down like this. Sorry, so this is M plus Z2. Sorry, plus delta MZ. Delta M, sorry. So we just rewrite like this, all the variable like this way. Then at the end of the day, what we have is water F. I already omitted R. So then everything R. I think, okay, maybe I can just keep R now. Plus, everything R. Sorry. Yeah. Psi bar R, I slash minus M R minus E. Psi bar gamma mu psi R mu R. Sorry, this is R. Okay, R. So this is, I just pick only one part. Okay, one part of Z. Pick one part of Z, and then the rest of the part is given by minus quarter delta 3 F mu R square plus psi bar I times delta 2 partial slash minus delta M. Okay, delta M psi bar R and minus E times delta 1 psi bar gamma mu psi and mu. Sorry. So you can split the bare Lagrangian into the two part. If you change if you do the following change of variable, okay, following change of variable, then this is indeed, this splitting is very meaningful one, and this is physical mass. This treated as a physical mass. Physical mass means the mass observed at our ordinary scale. Okay, this is the electron is a physical electric charge which is measured at our ordinary energy level. Or whatever, LHC, or it depends on energy, but energy scale, the mass measured at your energy level. And then this part is extra part. So this part is extra part, or part of bare Lagrangian. Lagrangian. This is the first part. Let's use the purple one. So purple one is physical Lagrangian. Okay, so this is physical mass. Physically meaningful. Physical quantity, physical quantity measured at your scale, your energy scale. Scale. And this is physical Lagrangian. This is physical Lagrangian. Lagrangian. And the cost of the difference between real Lagrangian and physical Lagrangian, there is a cost. Okay? There is a cost. Okay? This cost indeed coming from all the high energy or quantum correction coming from this kind of loop diagram. Okay? This kind of loop diagram. So in fact, if you zoom into the very, very small, tiny scale, this kind of quantum correction, lots of quantum correction you will receive if you go to the really small energy scale. But you cannot measure. I mean, you cannot measure this kind of quantum scale, all the quantum correction simultaneously. You have to really go into the high energy. So therefore, this Lagrangian is given by high energy, and the low energy. The difference between low energy Lagrangian and the high energy Lagrangian is given is absorbed in the second term, and this delta is called counter term. So this delta is called what was that? Delta I are called delta I are called counter term. Delta I is of course I runs for 1, 2, 3, 1, 2, 3, and then also I delta M called counter term. And this counter term includes all the high energy contribution. Okay? High energy contribution. So therefore, so what we need to do is that the compare between the high energy and low energy and get rid of it. Okay, so I think maybe. So compare with high energy and low energy and get rid of the extra, all the high energy contribution we cannot measure. That's the idea of the renormalization or the how to say quantum correction. Okay, so that's what we are going to do. And this delta often includes the infinity. So the infinity, but there's a way to avoid infinity, so-called dimensional regularization, Pauli beta. So first we will learn how to incorporate this infinite, regulate this infinity that appear in delta by using so-called Pauli beta regularization, and later we will use dimensional regularization, which is introduced by essentially at Hooft and Beltman. So that's what we are going to do. And then first diagram we are consider is that the so therefore the main thing the rest of the lecture today is lecture 8, 9, and so on. The rest of the lecture, I think there's a seven lecture left or something like that. I don't remember. 6 or 7 lecture left. So what we are going to do is essentially we will measure this Zi. We will evaluate Zi and delta I, or delta M, whatever. We will compute this quantity, and then we will learn how to get rid of this delta, And what's left is physical quantity M and E. But still, it knows about some loop diagram quantum corrections. That's what we are going to learn. And then the first one is, of course, as you already know, if you read the lecture note, anomalous magnetic moment. So often, so in the Peskin-Schroeder, lambda will appear. So this one is at defined as lambda. And this one, the first one is physical Lagrange is measured at the energy scale is equal to mu. And this energy scale is equal to the Lagrangian. E is equal to lambda. And then second one is the difference between lambda and mu. Lambda and mu. That's an encoder encounter term. Okay. So that's the philosophy of the renormalization. Philosophy. And then, so next lecture I'm going to do is the derivation of anomalous magnetic moment. So we will evaluate this kind of diagram, which up here is U bar P prime, and then gamma mu P prime. And this is Q, and P prime and P. And then this gamma mu has something in the form of gamma mu plus delta gamma mu. And then this delta gamma mu will give you some, if you compute this delta gamma mu very carefully, so this G anomalous magnetic moment has 2 plus 1 plus so-called F, I forgot, F1, 2, I think, I'm sorry, as far as I remember 2. I think this is called form factor, which we are going to evaluate. And then this 2 plus some correction. This correction will give you the what shrink of first compute, and then then due to thanks to that he got a Nobel Prize. That's what we are going to do. And then I'm running out of time, so I'll stop here. Any question at this moment? So from here, I think it's 6 and 7 lectures are left. So the goal is to essentially evaluate this VI or delta I or whatever. So that's our goal. I think you moved the camera. I think camera is moved.